In this video, I'm going to show how you can do a logistic regression in JASP. This is the data we're going to be looking at, and you can find this in the link below the video. What we want to predict is whether people think that reclining seats on planes should be banned. People seem to have very strong feelings about this, and a lot of people hate it if somebody in front of them will recline the chair. So we want to see what variables predict this. And this is our dependent variable. Because it's a logistic regression, it's coded as zeros and ones. 0 means I don't think you should ban reclining chairs. 1 means I think they should be banned. And then we've got 3 predictors which I believe may be associated with this. Here we've got participants' height in centimetres. So the idea behind this is taller people may be more likely to want to ban them because they have less space. How often is an ordinal variable, which is how often people fly. And what we are looking at in this variable is basically an ordinal variable. Low scores means you almost never fly, you fly once a year. Higher scores mean you're a very regular flyer. And finally, we've got a categorical predictor called used elect. And this is basically asking participants if they have used electronics on a plane when they've been specifically told not to. So 1 means they have used electronics when they've been told not to. 0 means they've never used electronics when they have not to. So I'm going to see the extent to which these 3 variables, how often, my ordinal variable, used elect, my categorical variable, and height, a continuous variable, predict the likelihood of people wanting to ban reclining seats. So what we need to do is run our regression. So we go to regression and we select logistic regression under classical because we're not doing a Bayesian model, we're doing null hypothesis significance testing. And it's quite straightforward. We need to tell it what our dependent variable is, which is ban recline. Our covariates, we can put our ordinal variable of how often and height, which is ratio, can be put in there. And then use electric is a factor, is our categorical variable. And this produces our basic output. I'm also going to ask for right now, I'll come back to a few extra things, a confusion matrix as well. Let's have a look at our output. So this is our overall model fit. This is our model summary. So the first line is the null model, model 0, which is essentially in logistic regression, best guess. The null model predicts everybody's in the largest group, and here's our model with predictors in it. If you want to work out if our model is statistically significant, we need to look at these 3 statistics essentially here. We have our chi-squared statistic, our degrees of freedom, and our p-value. And our model is overall statistically significant. These values here, the AIC and the BIC, are other ways of assessing model fit. They don't come with a p-value. Basically, smaller values are better. On their own, the values mean nothing. But the smaller the IC and the smaller the BIC, the better the models. In both cases, the AIC and the BIC for the model with predictors is better. Generally speaking, if there's a difference greater than 5, certainly greater than 10, you would say one model is superior than the other. So based on the AICs and the BICs, we can also make a decision that our model with predictors is better than our null model. We also have 4 pseudo R-squared values. I am not a big fan of these. I think they make people think about logistic regressions in a funny way that I don't think is very sensible. We've got McFadden, Nagelkerk, Jaw, and Cox and Snell. I would recommend reporting probably one of these 3. I tend to avoid Nagelkerk. As you can see, it's a lot higher than the other ones. It tends to be quite optimistic. McFadden and Cox and Snell generally are the 2 I tend to report. We're just going to skip the coefficient table and just go down to here. This is performance diagnostics. This tells us our correct classification rate. So basically what this tells us is we've got observed column, so this is whether people in the data wanted to ban recline or not, and this is what our model predicted, whether they wanted to ban recline or not. The percentage correct our model gets is 70.19%. So it correctly classifies our predictor just over 70% of our participants. And we can look at these values here. So this 427 individuals, these people all did not want to ban reclining seats, and our model predicted that they would not want to ban reclining seats. So these are true negatives. These 65 people here want to ban reclining seats, and the model predicted they would want to ban reclining seats as well. So this is a true positive. So these are correctly classified. These 174 wanted to ban the seats reclining, but the model predicted they wouldn't. So they are a false negative because the model said negative, but they were positive. And these, the model predicted they would want to ban reclining seats, but they didn't. So these are a false positive. Overall, that gives us our percentage correct of 70.19%. We can also look at our individual predictors as well. Now, we have our regression coefficients. For every 1 unit increase in the predictor, how much the log odds of you being in group 1 change. That comes with a standard error as well. I'll skip over that for a second. We also get our WALD statistic, our test statistic, and a p-value as well. However, generally speaking, we don't often report the estimates here or unstandardized regression coefficients. Why? Because people don't think in terms of log odds. Instead, we report our odds ratios instead. So if you get an odds ratio above 1, that means that higher scores mean you're more likely to be in group 1. So people who fly more often are more likely to want to ban reclining, because ban recline is coded as 1. So class 1 is they want to ban reclining seats. Height had a positive association as well. Our odds ratio is greater than 1. That means that taller people are more likely to want to ban reclining seats. And used electric is 1. So people who use electric products when they shouldn't have, you can see our odds ratio is less than 1 here. So that means that the group people who use electrics are less likely to want to ban reclining seats on planes. We can see all 3 of those are statistically significant. We don't write up the intercept. Generally speaking, with our odds ratios, we'd also want to report confidence intervals with them as well. So we can just tick that box there. Let's just move that back so we can see a bit better. These are our confidence intervals for our odds ratios as well. You'll note, because they're all significant, none of them cross 1. These are both less than 1, and these 2 are both greater than 1. So that's how you can do your basic logistic regression in JASP. We're just going to cover 2 more things very quickly. We can look at multicollinearity diagnostics. So we got our tolerance and our variance inflation factor, which are just the sort of opposites of each other. So if your VIF's greater than 3, you may have some multicollinearity. Greater than 5, probably. Greater than 10, it's likely to be causing some severe issues in the model. And as you can see, all the VIFs are very near 1, so we don't have any problem whatsoever with that. We can also ask for case-wise diagnostics. So what this does is basically flag people who really don't fit the model very well. So if their standard residuals are greater than 3. So basically, that's one way of assessing sort of very outlying cases, people who don't fit the model well. Some people delete participants based on this. I certainly wouldn't. I'd only use it maybe to check if you've got a data entry error. In this case, we've got no influential cases found at all. So influential cases are people who don't really fit your model and cause a big effect on the model. So one person having a large effect on the model. Again, because this is a very large data set, it's unlikely to get anything that's going to have a big effect on your model. With smaller data sets, that can be a bigger issue. So there's lots of other bits that you can do, but that's your real basics logistic regression in JASP.